what you'll notice is as we put in more and more rectangles, we're going to get closer and closer to the actual area. When you're looking for the actual area, what you're doing is you're finding a definite integral. Let's look at a situation a little bit more general. We have the function y equals f of x, that's our blue curve, and we're putting rectangles inside of this curve so we can get estimates of the area. Sometimes we pick our rectangle to touch on the left-hand side, sometimes on the right-hand side, sometimes in the middle, but if we pick a value of x called x sub I that falls between a and b, we can make sure that when I put that x sub I into the function, it gives us the height of the rectangle. We just are not necessarily sure where that x sub I lies in here because it could be on the left-hand side, the right-hand side, the middle, or something in between there. But when I take that value x sub I and put it into the function, it gives me the height of the rectangle. So that means f of x sub I is the height. We get that from putting x sub I, which is right here, into the function, and the width of the rectangle, we're going to call that delta x. So in general, the area of this rectangle, which we'll call the ith rectangle, will be f of x sub I high and delta x wide. So remember, the f of x sub I gives me the height, and the delta x gives me the width. So we're going to have lots and lots of terms like this. We're going to have however many terms you want, corresponding to however many rectangles. That means that our area from x equals a to x equals b will be approximated by a bunch of rectangles. Here I'm saying n rectangles. So it'll be f of x sub 1 times delta x, that'll be the area of the first rectangle. F of x sub 2 times delta x, that'll be the area of the second rectangle. F of x sub 3 times delta x, that'll be the area of the third rectangle, and we'll do that till we get to the very last rectangle, the nth one, and that'll be f of x sub n times delta x. Depending on where we choose these x's, we can get left hand, right hand, midpoints, or something in between for our estimates of our sums. So those terms we need to be very careful with, because each one is going to tell us something about this sum, the area of a particular rectangle. If we add them all up, we get our estimate of the area, and what we know that the more of these rectangles we use, usually the better the estimate. But right now we've got a sum of n of these rectangles, and what I'm going to do is I'm going to abbreviate that using this sigma notation, this big Greek letter sigma. What this tells me is I have many terms, each one which is f of something times delta x, and the sigma tells me that I'm adding many of these things up. I've put in x sub I here to represent the different x's that I have here, the things that change. It says I'm going to take a sum, so Greek letter sigma, where I is equal to 1, so that's going to put I equal to 1 into here. That gives me the first term. And I'm going to take that sum all the way up to n, because when I put n in place of I, that gives me the last term. If I use everything from I equals 1 up to n, that gives me this entire sum of however many terms that I have here. So the exact area is found by using as many rectangles as I possibly can. And I'm guessing you might have figured out where we were heading here. If you let the number of rectangles get infinitely large, so you take the limit as n approaches infinity of this sum, I equals 1 to n, f of x sub I delta x, what we'll get is the exact area. This limit is called the definite integral of f of x from a to b. So our blue box here says if f is defined on an interval a to b, the definite integral of f from a to b is symbolized by a definite integral, and now notice that we've put A to B on here, that tells me that the area that I'm finding goes from A to B and is under f of x. The dx tells me the variable that we're working with. So this symbol here is just another way of saying exact area. And the way we do that is we take many, many areas of rectangles, in fact, an infinite number of rectangles, and we sum them all up. As long as we can do this limit, then we can go ahead and find the exact area. Remember that delta x is the width of each rectangle, and f of x sub I is the height of the ith rectangle.